All right, for lesson 4.1 for algebra, we are just starting to look at graphs as representations of two different quantities and how they can relate. So let's take a look at number 1. It says the graph below shows the volume of air in a balloon as you blow it up until it pops. What are the variables? Describe how the variables are related at various points on the graph. Okay, so let's first talk about the variables. What we have on our horizontal axis or our independent axis is time. So one of the variables is time. So time, and it is on our independent, it's on our horizontal line. And anytime you have a horizontal line, we are talking about it being an independent variable. Okay, the other variable we're talking about is volume. So the volume of the air that's in the balloon as you blow it up. So volume in this situation is our y-axis, which makes it our dependent variable. Okay, so then it says describe how the variables are related at various points. So here's what I'm seeing. I'm actually going to use my highlighter and we're going to kind of tell a story as this goes on. So we haven't started yet. It's 0, 0. We start at the origin. And slowly time starts to tick by. And as time starts to go, our volume starts to increase. So we're blowing it up after a few seconds. And then look what happens. It levels off. It becomes constant for just a little bit of time, for just from here to here of time. So I hope what that means to you is that for this amount of time, you're probably taking a breath. The volume in the balloon stopped rising and stayed constant because you're taking a breath. And then what happens? After a little bit more time now, more air starts to go in. The volume increases in the balloon. And then it becomes constant again because you're probably taking another breath. And then it rises again and sinks just a little bit and then rises one last time. And then all of a sudden, look at the volume. Look what happens to it. It drops to 0. So I'm not sure how much time has elapsed, but more volume, constant volume increases volume, and then it goes to 0. So this is the moment that the balloon pops. So once it pops, right here, the volume goes back to 0. Okay, let's take a look at these got it examples and see if that makes sense to you as far as something else. So what are the variables in each graph? The variables in our first graph are length and time. I don't really know what board length means, but maybe you are, we can just make this up. Maybe you are crafting something. You're in the industrial tech lab and you've got a board and you're sawing pieces of it off in order to build something. So the length started really pretty tall. Like here's 0. So we'll say, I'm just making up a number, but let's say that number's 10. So the length is maybe 10 feet long. And then it stays 10 feet long. And after a certain amount of time, the length drops off. And then there's a little bit more time that goes by and the length drops off again. And then a little bit more time goes by and the length drops off again, and then more time goes by and it stays the same. It stays constant. So maybe you are cutting pieces of a board and then finally you get to the point where the time doesn't matter because you're not cutting it any longer. Let's look at B. B makes sense because all of us probably have a cell phone. We're talking about the cost of our June cell phone cost, the bill from the month of June. So here's how expensive it was. We know it wasn't 0, 0. It wasn't $0. So for June, it started at, let's say that's some easy number to think of. Let's say it's like 100. So you have lots of minutes of calls. You're calling your friends. Your bill is still 100. It's still 100. It's still 100. It's still 100. And then after a certain point in the month, maybe your cell phone company says, okay, you've started to go over the number of minutes. Maybe this is 1,000 minutes. I don't know. I'm just making this up. So as soon as you start to make more calls that increases closer to 2,000 minutes, the cost of your bill is going to start going up. So it is constant for a long time until you reach a certain amount of minutes, and then all of a sudden your bill starts to increase. And once again, in this one, the variables are the minutes of the call and the cost of the call. Okay, let's take a look down here at trying to match a table with a graph. So here's a table off to the side. This is a table. They are video downloads. So what's happened is a band has allowed fans to download its new video from its website. The table shows the total number of downloads after 1 day, after 2 days, after 3 days, and after 4 days. This is how many downloads it has had. Which of these 4 graphs could represent the data shown in this table? So on day 1, we're looking at 346 downloads. So really, day 1, that could be, we just don't know what it's doing yet. That could be or that could be. But what we need to do is look at day 2. Day 2, it more than doubles. It actually just about triples. So 300 times 3 is 900. So it's over 300, so it's over 900. It's probably just about 3 times. So this one is definitely going up. So it could be B. This one's going up. It could be A. This one's going up. It could be C. However, this one is going down on the next day. So we know it's not D. All right, let's look at day 3. Day 3, it more than triples again. So we are not seeing a constant amount. We're not going up 300, 300, 300. We're going up 300 and then more than 2,000 and then more than 6,000. So we are looking at a very exponential growing graph. It's jumping a lot faster than something that would be linear like this one. Linear is a straight line. We're going up a constant amount each time. So it's definitely not going to be A. C looks like it goes up a lot and then just a little, and then it's kind of starting to flatten out. And that is not what we see happening here. We see it continuing to grow hugely by day 4. So it's not going to be C either. So we know that our answer is B, but let's make sure you understand that this goes up and then it goes up drastically more and then drastically even more again. So it's more of a curved graph. It's not linear. It's more exponential in growth because it fits our numbers that we have in the graph. All right, let's look on the back. So this table shows the amount of sunscreen that you have left in a can based on the number of times the sunscreen has been used. So if you use it 0 times, there is 5 ounces left. Once, you're down to 4.8. Twice, you're down to 4.6. 3 times, you're down to 4.4. So which of these graphs could represent that data? First of all, I want to remind you that our variables are, our horizontal variable is our independent variable. So independent variable goes here. And then dependent variable goes up this side. And the reason that that's how that is in math is because the amount of sunscreen depends on the number of uses that we have it. So if this variable is dependent on this, then that's what makes it our dependent variable. So the amount of sunscreen depends, it's dependent on the number of uses, which the reason the number of uses is independent is because we don't know how many times you used it. Like you could use it a few, you could use it a lot. It's independent of anything else. But the amount left in it depends directly on how many times you use it. So let's check. All 3 of them appear to be going down, so we know any of them could work. But let's see if this is a linear amount. Let's see if it's a constant amount. From 5 to 4.8, we're subtracting 0.2. From 4.8 to 4.6, we're subtracting 0.2 again. And from 4.6 to 4.4, we're subtracting, 0.2 again. So we are going down the same spacing, the same amount of steps each time. So when you look at something like this, you're going down a lot, and then a little, and then a little again, which is not constant. It's a curve. So that is not going to be our answer. This one looks like it is going constant. However, at our 4th time, are we out of sunscreen? This one ended at 0 on amount of sunscreen. We have none left. And after 3 uses, it should still have 4.4 ounces left. So we don't want to be empty. We don't want to go out and get all the way down to 0. So this one is not going to be correct either. So we know that it's C, but it's because this amount is the same amount of spacing as this amount, which is the same amount of spacing as this amount. It is a constant amount as we go down. And we're not out. After 4 uses, we still have 4.4 ounces left, so this is the only one that works. All right, let's do a real quick lesson check on today's lesson. What are the variables? And use it to describe it. So the variables are car weight, which is independent, and the amount of fuel that's used that is dependent. So independent, dependent. So what they're saying is a car's weight is going to start here. A car's weight's never going to be at 0. Car always has a weight. So let's say that a car's weight starts at, I don't know, 1,000 pounds. I have no idea. Maybe it's a smart car. The heavier the car, so that as the weight increases, as let's say this is 1,000 pounds, and this is 2,000 pounds. As the weight increases in the car, the amount of fuel it uses increases. So that is how the variables are related. The heavier the car, the more fuel it will be using. Number 2, describe the relationship between time and temperature. It looks to me like 1 hour afternoon, so at 1 o'clock in the afternoon, it's 61 degrees. At 3 o'clock in the afternoon, because this is time and number of hours afternoon, so at 3 o'clock it's up to 62 degrees. But then look what happens. At 5 o'clock it drops down to 58, and then at 7 o'clock it drops down to 51. So this would be a graph that would look something like this. It would start off slowly increasing, and then it drops pretty much off. So describe the relationship between time and temperature. So time would be independent. The temperature depends. So the temperature is dependent on the amount of time it is past noon. So the relationship is that time would be independent, temperature would be dependent, but really the relationship is the hours that are past noon steadily increase in temperature until we get to about 4 or 5 hours past noon, and then temperatures start to decrease again. All right, last one. Match one of the labeled segments with rising slowly, match one of them with constant, and then match one of them with falling quickly. So let's look at A, B, C, D, and E. One of these is going to match with rising slowly. One of them is going to match with constant, and one of them is going to match with falling quickly. So I hope that you realize that both A and B are rising, but which one would be considered to be rising slowly? A to me seems like it's rising a little too quickly. So I would match rising slowly with B. Constant means it's not changing. It's staying the same over time. So I would say this would be our constant because it is flattened out. And falling quickly. So D falls, but so does E. And which of them is falling more sharply, more quickly? I would say that the quicker one is definitely the D, because E is still falling, but not quite as fast. And our very last question says, describe a real-world example, relationship that could be represented by this graph. So see if you can think of one. The only thing I have in my head right now is back to these temperatures, because in a hot summer day in the morning, the temperatures as soon as the sun comes out could rise quickly and then rise a tiny bit more, and then it's going to stay maybe like 95 or something. And then in the evening when it cools off, maybe it drops drastically to 70 and then even goes down to maybe 60. Just depends. So what I'm thinking of as a real world relationship is temperature. But I kind of cheated because that's what I have in my head from this previous problem. See if you can come up with another one and write it out for me.